This is problem 26 from the induction section. The 5 centimeter square loop at right consists of 100 turns. So I'm going to put that area down right away with the times 100 so I don't forget about the number of loops. Is located in a 0.1 Tesla magnetic field. So initially we have a 0.1 Tesla magnetic field and it's pointed into the page, which is the negative k hat direction. Then the polarity of the magnetic field is reversed, which means the direction changes. So afterwards, we still have the same magnitude, but now the magnetic field's pointing out of the page. And the bulb's resistance is 30 ohms. I have Faraday's law and Ohm's law to use, and I want to know over what time interval must the reversal take place in order to supply the 10 milliamps necessary to light the bulb. So I'm going to skip the qualitative analysis, and I'm going to see if I can figure out the direction of the induced current just based on paying attention to the signs, which we talked about in one of the previous videos. So to do that, I have to define the positive or the direction that the area vector is pointed in. So let's say the area vector is pointed out of the page. Then initially, the magnetic field's pointed into the page, so my initial flux is going to be negative. I don't think we need to write that down for the sake of solving the problem, but let's do it anyways. So the initial flux is equal to B initial dotted with A. So that's k hat and negative k hat, so I have the negative sign, and then it would be 0.10 Teslas times 5 centimeters squared. You should change the centimeters to meters at some point, times 100. So there's my initial flux, and it's negative because of how I defined the area vector. Okay, then I'm going to say the EMF is equal to the negative derivative of the flux with respect to time, but we're going to assume that the magnetic field is changing linearly, like we saw in the previous problem. So this is the change in flux over the change in time. Okay, if you think back to Physics 161, we had the velocity is equal to the change in position over the change in time if the velocity was constant, which means the position versus time graph was linear. So then it gives you the velocity. But if the position versus time graph was not linear, so let's say it looks like this, then doing delta r over delta t instead of the derivative, it doesn't give you the instantaneous velocity, but it does give you the average velocity. So if we're not told how the current is changing, we're going to assume that it's changing linearly, like what we have here. But if it's not changing linearly, that would give us the average EMF, which is the best we can do if they don't give us any more information. Okay, so we're going to say it's the change in flux over the change in time with the negative sign in front, which is the final flux minus the initial flux with the negative sign that I almost forgot out in front over delta t. I have the initial flux here. What's different with the final flux is just the sign, right? Because it has the same magnitude, but now it's pointing in the k hat direction. So the final flux would be the same thing, but it would be positive. So if the final flux is positive and the initial flux is negative, then the final flux minus the initial flux will be the same thing as twice the final flux, because they have the same magnitude, just the opposite sign, and since it's the initial flux, which is negative, when you subtract the initial flux, that's the same as adding the final flux over delta t. And that gives us something negative for the EMF. I'm looking for the time interval. and I can say the EMF is equal to I times R. Okay, let's pretend for a moment that I'm looking for the current. If I was to divide by the resistance, which is always positive, I have delta T here, which is positive, and the final flux, which I said is going to be positive. So that means the current is equal to something negative. That I can use to figure out the direction of the current. So I said the positive direction for the area vector was pointing out of the page. So if I get a negative current, the current must be, if I put my thumb in the negative direction, going this way. So that tells me that the current is going this way. So because I skipped the qualitative analysis, now I can actually use the signs in my solution to figure out the direction of the current. But I should go back now and make sure that agrees with what I would have gotten if I used Lenz's law to figure out the direction of the current. Okay, so if the magnetic field is initially pointing into the page and then later it's pointing out of the page, at some point the magnetic field must be zero. So initially we have a flux, and then halfway through the flux is going to be zero because that's when the magnetic field is going to be zero. So initially the flux is decreasing, which means that your induced magnetic field should be pointing in the same direction as the magnetic field that you had initially, which would give you a current this way. And then after we pass through zero, the magnetic field is increasing, but now it's pointing out of the page, which means the flux is now increasing with the magnetic field pointing out of the page, which means the induced magnetic field should still be pointing into the page, because now it wants to counteract the increasing magnetic field which is pointing out of the page, which gives us a current flowing in the same direction. So all is well, and now I can proceed to find the time that I am looking for. Okay, so now that I have taken care of the sign, I'm going to forget about the negative sign and say something like absolute value of the current here is equal to absolute value there. And so the current's 10 milliamps. So I have 10 milliamps times the resistance of the resistor, which is 30 ohms, is equal to twice the final flux, which would be 0.10 teslas, times 5 centimeters, which you need to convert to meters, times 100, divided by delta T. And you're going to solve for delta T, and you can take a moment to try and do that. And the answer that you should get for delta T is 0.167 seconds if I did everything there correctly, and it looks good. So this is what you should get. Okay, so I hope I didn't confuse you too much with the signs here. But basically what I wanted to show you is you can use that to get the direction of the current here, but if you don't care about the direction of the current, then the sign is no longer important, and you know delta T should be positive, so then you can just ignore the sign and look at the magnitude and you can find delta T. Okay, but it's always a good idea to check to make sure that the direction that you put down for the current agrees with what you have based on the signs in your solution.